Hello and welcome, everyone. It's great to have you here for the first virtual public observing night of the fall semester here at the University of Iowa. And I'm so glad that you all could join. I'm here in Iowa City. We'll be controlling our telescope in Arizona tonight. And here with me, I have a few different undergraduate students who are going to observe these targets in the night sky for you. We will look at a few different targets, but before we do this, I'm going to give you a view of what the sky looks like tonight. And we're also going to have a talk about the sky and the planets that we'll see in the solar system. And this will be given to us by another undergraduate student who's joining us remotely. So first, let me show you a little bit about what we'll be looking at tonight. So if you were to go outside right now and look at the sky, this is what we'd see. Here we are in Sonoyta, Arizona, near Tucson, Arizona, at the Weiner Observatory, of which the Iowa Robotic Observatory, owned by the University of Iowa, is a part. So if we wait a little bit of time, Cole Dorman is going to give us a talk for about 15-20 minutes, or maybe a little less. But let's bump the night a little further along in Arizona. This is what the sky will look like in just a little while. And we can also, with the power of technology, we can see a little bit more of what is in the sky above us. A lot of constellations, right? If we look to the south and the southwest, we can see two bright objects in the sky, Jupiter and Saturn. And we'll look at both of these targets tonight. Additionally, though, if we look at just going to search for it. Well, in the constellation Aquarius, oh, there we go. In the constellation Aquarius, we have the planet Neptune. And we'll be looking at the planet Neptune tonight as well. Not sure why it wasn't coming up, but now we have it. In the constellation Aquarius is the planet Neptune. And then finally, our first target of the evening is actually a comet, which is in the constellation Ophiuchus. So if we look in the southwest sky, just west of Saturn and Jupiter, we can see the constellation Ophiuchus, the water carrier. And this is where the comet we'll be looking at tonight is. And so with that, I'm going to turn things over to an undergraduate student, Cole Dorman. But before we do, I'm going to ask everyone one question before we get started talking about the planets and the rest of our solar system. So if you would share what your favorite planet is. And while these results are coming in, I'll share the song that we got to hear before the event started was by an a cappella group called the Chromatics. This is a musical group of some professionally trained astronomers, teachers, engineers that love to sing about physics, astronomy, space, and a whole host of other things. All right, let's check out the answers to this poll. So everyone loves Earth, which is a great choice, and Mercury gets no love. But it'll be great. We'll get to see Jupiter. The second favorite planet is Saturn, and we'll get to see that tonight. So that's pretty exciting. Okay, so with that, Cole, would you take over for us? Cole Dorman is a physics and astronomy major at the University of Iowa, and he's the president of the Society of Physics Students Club.
Hello, everyone. Let me share my screen real quick. I hope you guys are all having a wonderful night. Oh, hold on. Not working with me too well. All right, here we go. So tonight we're going to be going over the solar system and everything about that. And so what perfect place to start the solar system than the sun? Sun's right in the very middle. We all orbit the sun. Every planet orbits the sun. And something that's pretty apparent about the sun is it's extremely hot. It's about 10,000 degrees Fahrenheit on the surface. And so many people think of the sun as a massive ball of fire, but I kind of like to think of it as just a massive ball of explosions or fusion. And what this fusion is it's the atoms and molecules in the sun that's ramming into each other to give the sun energy, and this energy is coming off in the form of photons and heat that heat up the Earth and all the other planets. Now, the sun shoots off a lot of stuff that comes into contact with the planets, and this stuff is called solar wind. And so solar wind is a gentle outflow of gas. Now, when I say gentle, it's gentle in terms of the universe, but by our standards, it's still pretty powerful. The sun is a pretty powerful object, not something to be taken lightly. And it shoots out this gas in all directions from the upper atmosphere, which is called the corona, pretty aptly named. And so it's weird to think that stars have an atmosphere because we have an atmosphere. And so it's the star's atmosphere and the sun's atmosphere is not like our atmosphere. In terms of you can't really get down this, you don't want to get on the surface of the sun and breathe what's got going on, but it still does hold gases like we do. And so our atmosphere holds oxygen, its atmosphere holds a bit of different stuff. But solar wind is what creates the tail that we see on comets. And so we'll talk about comets a little bit later. But the wind is pushing on the comet and it's creating this tail, this long tail behind the comet. This tail comes from the solar wind. Now, the sun, like I said before, is the center of the solar system, and it's the heaviest object in the solar system by far. It's about 330,000 times heavier than Earth, and it accounts for 99.9% of all of the mass in the solar system. It's 109 times wider than the Earth. Now, the next planet, the first one out from the sun, Mercury, didn't get much love from you guys, but that's okay. It's the smallest planet and it's the innermost planet. And so a year on Earth is 365 days. It takes 365 days for the Earth to make one orbit around the sun, and that's what we call a year. Well, Mercury has really small years with the sun. A year is 88 days on Mercury. So you're going to be a lot older if you go onto Mercury than you are here. And Mercury is tidally locked with the sun. Now, what does tidally locked mean? It means that its face is always facing a side of Mercury is always facing the sun. And so the moon is tidally locked with Earth. We only see one side of the moon. We never see the so-called dark side of the moon, which isn't actually dark, but it just doesn't get any light from the sun. But unlike the moon and Earth, Mercury is tidally locked 3-2 with the sun. So for every 3 orbits Mercury makes around itself, it orbits twice around the sun. So the sun actually does see other sides of Mercury, but it makes the one side of Mercury really hot that it sees for a long time. The next planet out is Venus. And so Venus is the second planet from the sun. And it's very similar size to Earth. And Venus has the longest day in the solar system. Now, it's the hottest planet in the solar system due to its thick atmosphere. And so you might be thinking, how is it the hottest planet if Mercury is closer? Well, Mercury is so small, it doesn't have much of an atmosphere. It doesn't have that gravitational pull in order to keep that gas, in order to keep that heat onto it. So what Venus does is, because its atmosphere is so thick that when this heat comes onto Venus, it can't escape as easily. And so it almost like the atmosphere boils itself. And so that's how it gets so hot. Now, the third planet from the sun, oh, all right, there we go. Third planet from the sun is us, it's Earth. And so some unique things about Earth is that we hold light, or life, not light. We hold life. We don't know any other place that holds life like we do. Another interesting thing is that Earth has an active core. Our core is made of molten lava. We have the tectonic plates that move around. You don't really see that a lot in other planets in the solar system. Now, next we have Mars. Mars is the fourth planet of the sun. It's the second smallest planet in our solar system. And that's the planet that we've sent rovers over to. The Curiosity rover, you might have seen in the news, things like that. And so Mars has a lot of craters. Like our moon has craters, a lot of asteroids crashing into Mars, meteorites. And another cool thing about Mars is that it has polar ice caps like Earth, but its polar ice caps are underground. Ours are above ground, but Mercury can't really have any water or ice above ground because its water evaporates due to low pressure. There's not much pressure on the surface of Mercury, so any water that's there, it evaporates. That doesn't mean that there never was water there. It used to have giant oceans, lakes, and rivers like we do here on Earth, and we can see that in the geology on the surface. Now, the next thing out in the solar system you'd think would be Jupiter, but no, it's the asteroid belt. And the asteroid belt is primarily between Mars and Jupiter. And like you see in a lot of movies, there's this image. This is an artist depiction that we're looking at. This isn't the actual asteroid belt. But even this artist depicted that the asteroids are very close together. You see that a lot in movies. But there's actually a lot of space between asteroids. And about half the mass of this asteroid belt is only in 4 asteroids. That's Ceres, Vesta, Pallas, and Hygiea. And Ceres is so large that it could be a dwarf planet. But asteroids can get so small that they can be the size of grains of dust. So there's a lot of range in size between these asteroids. And so these asteroids are made up of planets that never could really form. We'll talk a little bit more about planets forming and planetesimals and particles and stuff like that at the very end. So, but what you just need to know is that asteroids were planets that were planetesimals that wanted to be planets, but just never could really make it. Now, next thing out, I kind of spoiled it a little bit, is Jupiter. It's the 5th planet from the sun, and it's the largest planet. It's a massive planet. And so a big feature of Jupiter we see is this red dot right here. It's called the Big Red Dot. And the Big Red Dot is a centuries-old storm. It's a massive storm. We think our hurricanes are here bad, like in Florida and things like that. I wouldn't want to be there. It's a not very fun place. And so unlike Earth and Mars and Venus or Mercury, which are called terrestrial planets, are made of rock, Jupiter is a gas planet. So it has a very small, tight core, but most of it's made of gas. So you can't walk on the surface of Jupiter. You'd fall right through it into the center, and that wouldn't be fun for anyone. And so Jupiter is mostly made of hydrogen and helium gas. But because it has all this gas and it's able to attract so much mass, it has a lot of moons. Here on Earth, we only have 1 moon, but Jupiter has 79 moons. And these moons aren't tiny either. Its largest moon, Ganymede, is so big, it's actually larger than Mercury is. That's pretty hard to wrap your head around, but that's just how big Jupiter is. And so the next planet and so Jupiter, like Dr. Robert said before I get ahead of myself, Jupiter is one of the planets that we're going to be looking at later. And the next planet in the solar system is Saturn. Now, we all know Saturn because it's massive rings. And so its rings actually aren't solid, but it's made of little tiny ice particles and rocks. And it has its own, we can think of its own little tiny asteroid belt. It's the 6th planet from the sun. It's the 2nd largest. And Saturn is also made of gas. These gas planets are known as gas giants. And it's because they're able to hold so much mass and so much gas into them. And so Saturn is another one of these objects that we're going to be looking at a little bit later tonight. And so next, we have the planet Uranus. And Uranus is the 7th planet from the sun. It's the 3rd largest, again, another gas planet. And a pretty cool fact about Uranus is that it rotates almost completely sideways. So we look at Earth, and Earth rotates on a little axis that's about 30 degrees off from being perfectly straight up. You see it on globes. Globes aren't perfectly straight up, but Uranus almost completely rotates on its side. But other than that, it's kind of hard to tell what's going on in Uranus. It's almost completely featureless. As we're looking at here, it's kind of just a light blue ball. Now, the next planet and the final planet in the solar system is Neptune. And so Neptune is the 8th planet from the sun. And Neptune has absolutely crazy long years. So like we were talking about before, a year on Earth is 365 days because it takes 365 days for the Earth to make one full rotation on the sun. Well, it takes 164 Earth years for Neptune to make its one rotation around the sun. Now, all these other planets that we were talking about have been observed through telescopes or just with eyes. If you look in the night sky, you can actually see Mars with your naked eye. You can see Jupiter and Saturn with your naked eye. And the other planets you can see just through telescopes, things like that. But Neptune is the only planet that was able to become predicted through math. It was not found through observations. What mathematicians and astronomers saw was they noticed that the path the planets were taking throughout the sky they weren't traveling the path that you'd expect them to be if there wasn't another planet there. And so they theorized with those planets, once we got the technology, we could see, oh, there is a Neptune. Now, Neptune is another gas planet, and it is another object that we're going to be looking at later. Now, the solar system isn't done yet. Next, we have the Kuiper Belt. And the Kuiper Belt is like the asteroid belt, but it's a lot bigger. It's about 20 times as wide, and there's about 200 times as much mass in the Kuiper Belt as there is in the asteroid belt. Now, the Kuiper Belt has several what we call dwarf planets, planets that aren't large enough, or bodies that aren't large enough to be a planet. And the largest dwarf planet being our friend Pluto. Everyone knows Pluto. Now, Pluto, like most stuff that we were just talking about, is not made of gas. It's made of ice and rock mostly. And another thing that you can find in the Kuiper Belt is comets. Now, we're going to be looking at a comet from the Kuiper Belt. And so comets that come from the Kuiper Belt make a relatively quick trip. Now, relatively quickly to us is a little bit different from relatively quickly in universe standards. Roughly quickly in the universe standards is about less than 200 years. Now, I don't know about you, but 200 years is a long time to me, but comets can take a lot longer than that. And finally, the last thing in the solar system is what's known as the Oort Cloud. Now, there's still a little bit of speculation about details of the Oort Cloud, what it is, and if it's even kind of real. But unlike all the other objects we were looking at, it does not rotate in a flat plane. It's a giant sphere surrounding our solar system. And it's like a bubble, but it's made entirely of just the rocks and ice. Now, comets that don't come around very often, that take a lot more than 200 years, come from the Oort Cloud. And so the Oort Cloud is the theoretical limit of our solar system. But I get we kind of went over a lot of information. So to kind of do a recap, I like to do mnemonics to kind of memorize the order of the planets. So here are some ones that I think are pretty funny or my favorite. And so it goes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And so if you guys have any ones that you think are pretty interesting, feel free to put it in the chat. But these are some of my favorites. Now, that's everything we covered here is the solar system, what we know today. But how did the solar system come to begin? Well, its story kind of started all around about 4.6 billion years ago. And so our solar system began as a nebula. A nebula is a large cloud of gas and dust. And I'll be going a little bit more into detail that with our next talk that we're going to be doing. But what you just need to know is that a nebula is a large just cloud of gas and dust. And so you might be asking, how did a nebula become a flat solar system? Well, tons of things are flat. How does just giant thing of gas become a flat rotating planet of stars and planets? We see plenty of flat things in the universe. Saturn's rings are flat. Black hole accretion disks are flat. Other galaxies and solar systems we see are flat. Well, when a nebula has enough mass, it collapses under self-gravity. Its own gravity takes it and just pushes it in. Now, under this self-gravity, it gets really hot and energetic. And through this heat and energy, it forms stars. But there's still a lot of dust and gas there is in this nebula. And so this leftover dust and gas compresses and becomes these small rocks that can get pretty large in size called planetesimals. And so all of these planetesimals and the star that we see in the center hold something that's known as angular momentum. Now, it's kind of a crazy word to think about, but pretty much it's just how fast something is orbiting. Now, every last particle holds a bit of angular momentum, and all these planetesimals are crashing into each other, all these particles are hitting each other, and eventually one direction wins out. So the top and bottom cancel out, and then one direction, maybe left or right, will spin around, and that's the direction that wins in this angular momentum battle. And so that's how that's how this giant cloud becomes this spinning solar system that we see that's on one flat plane. Now, it doesn't directly just go from gas to planets. And so we see this picture right here that kind of takes some snapshots of the process. But we have this gas cloud, and then this angular momentum starts to turn into this flat spinning plane. And then these particles keep crashing into each other. And so we got the star, and then it forms these planetesimals. And then these planetesimals, in turn, start crashing into each other, just like how the particles kept crashing into each other. And so these planetesimals will eventually create a mass large enough where it becomes a planet. And then this planet has enough gravity where it can start attracting planetesimals on its own. And so if it's all just planetesimals, then it becomes a terrestrial planet, which is like the first 4 planets we know in the solar system. But some planetesimals are massive enough where they're able to attract gas too. And so they keep getting more mass through gas. And so gas itself is pretty light, but when you get enough gas, it's able to hold a lot of mass on its own. And so that's how these gas giants become so massive. And so that's how we end up with the solar system that we have today. And so I want to just kind of take this time to see if anyone has any questions. If you guys want to type them out, if you want to unmute yourself and ask them, I'm happy to answer anything. Well, it's no worries if you guys have nothing to ask or anything like that. If you have any questions later, feel free to just type them out in the Zoom chat. I'll get around to them. But I want to thank you all for being a wonderful audience. I'm going to stop sharing. I'm going to give the floor back to Dr. Roberts. And I hope you guys have a great night.
Thank you so much, Cole. It's so wonderful to have you here, and I really appreciate your talk. Someone asks, what was the first planet? The closest planet to the sun is Mercury, and that was the first planet that Cole talked about this evening. I hope that answers your question, but if not, absolutely do. That was a very generous offer of Cole, and so he perhaps is just really going to be going through the chat, looking at people's questions, answering their questions. So please feel free to put your questions in the chat throughout the rest of the night. And once again, thank you so much, Cole. Okay, so I'm going to take us to our telescope in Sonoyta, Arizona at the Iowa Robotic Observatory. Here I am showing the computer screen at the observatory right near the telescope. And so we have a couple of different programs up here. One thing that we have is some software that points the telescope around. Down here, you can see a video feed of our telescope. And so if I point the telescope over here, you can watch the telescope move. This is the night sky up above us. We have all the stars. This is the horizon, low down in the sky. And where the telescope is passing through right now is directly overhead. The sky in the, directly up above is right here in the center of this circle. Over here on the left, as our telescope comes back to where it was, is some software that controls the camera of our telescope. So we can take pictures. As you see, we've taken this picture here of a few stars just to get us started for the evening. You can see what the telescope sees through its camera. And so just to speak a little bit about this telescope here, this is a 20-inch telescope. And when we say 20-inch, we're referring to the size of this mirror here in the back. Light enters the telescope from the sky and bounces off of this mirror. This is the primary mirror in the back, and then light will bounce off of it and come up here and hit our secondary mirror. It will bounce off again and travel through a hole in the primary mirror until it gets to our filter wheel and finally our camera, which are both on the back of the telescope there. And so let's take a peek at the sky one more time before we go to our first target of the evening. So again, just as we said before, if we've got the northern sky here, we can instead look to the south and we'll see Jupiter. And Jupiter in the constellation Sagittarius is our first target of the evening. And so I want to share another question with you guys. How many moons of Jupiter do you think we might be able to see with our telescope tonight? Go ahead and put what you think your answer might be. Okay, so a lot of people said 4 and 3, and these are great guesses. There are 4 moons of Jupiter that are known as the Galilean moons. Galileo looked up with his telescope, just as it was described in the song that we were listening to when the evening started, and he saw the 4 Galilean moons, so Io, Europa, Ganymede, and Callisto. And these 4 Galilean moons are very bright. They reflect light from the sun, just as all bodies, planets, and moons in the solar system do. They reflect a lot of light from the sun, and we can see them quite easily. So with any luck, we'll see all 4 Galilean moons tonight. Depending on the fact that the moons are going around Jupiter, so there may be some behind Jupiter or in front of Jupiter, so we might only see 3, maybe even 2, but there are 4 very bright moons of Jupiter, many of which we have a good chance of seeing tonight. So what we just did, you saw some graphs up on the screen there. It's important to make sure that the camera here on the back of the telescope is at the right position. We need to move it back and forth depending on the temperature of the night and some other factors. It's important to focus our telescope just as you might focus a digital camera before taking a picture. So that's what all those graphs were about. With that, I want to introduce you guys to Austin Dalsing. He is a cybersecurity major here at the University of Iowa, and he's going to show you guys Jupiter.
Thank you. Hi, I'm Austin Dalsing, and as Dr. Roberts said, I'm going to be showing you guys Jupiter tonight. So before we get any images of Jupiter, we have to slew this telescope towards the object that we're going to be aiming at. So I've got pulled up on my other device here the coordinates to slew to. These coordinates essentially think about GPS, except for the entirety of space. So we'll get these typed in here, and then you'll see the telescope move. And once that's all settled, we can pull up some images for you guys. So we've got 19, and 37. There we go. So as you can see on this diagram here, we're moving, and you can also see the live view of the telescope slewing towards the object. And there we go. So we seem to be right on it. So I'm going to go ahead and select the filter that we'll be capturing through tonight, which will be hydrogen alpha. There we go. And just let it load here. And we'll essentially be taking a 0.1 timed exposure so that we don't overexpose the image to get too bright of an image. So we still want to see the object here. So here we go. This dot in the middle is Jupiter. So we're going to pull up this to make it a little bit easier to see. Oh. Gotcha. There we go. All right, so these small specks next to it are actually the 4 Galilean moons that they mentioned initially. So they're all in a little line here, which is kind of fun to see because, as they said, they are rotating around Jupiter. So they're never in the same place. So these moons were discovered by Galileo initially in the 1600s with his telescope. These 4 moons are called Io, Callisto, Europa, and Ganymede. And each of these have their own really interesting qualities about them. For instance, Io, the closest moon to Jupiter, so it'll be right here. This moon is being stretched constantly by the gravity of Jupiter, and that in turn is heating it up. And all of this heat that is applied to this moon actually gives it active volcanic activity. So you've got all that heat stuck in there. And then going over, we have Europa, which is an icy moon. So it's got an entire surface of ice. And then underneath that surface, we have actually about 31 miles deep worth of ocean. So this is moving water that we have on a moon of Jupiter. And it actually has a slight atmosphere of oxygen. And then after that, we've got Ganymede, which is, as Mr. Dorman said, bigger than Mercury, the planet Mercury. And it is also very old. So it's got this cratered surface from impacts of objects around the solar system over the years. It's not dissimilar to our own moon, where you can actually see the craters from impact. And then you have Callisto, which is actually the oldest moon in the entire solar system. So Callisto is approximately 4 billion years old. And just like Ganymede and the other moons, it has a lot of impact craters, but it's got the most in the solar system because it's been around the longest and it's been hit the most. Yeah, And so these are the 4 Galilean moons that you can see here. And now on to Jupiter. So I'm going to try and slide this so that you can actually see some detail on Jupiter itself, if we can get it here. There we go. And then we'll try and magnify it. There we go. To bring it over a bit. And just a little bit more. There we go. Okay, so as you can see, here's Jupiter. As they mentioned, this is a gas giant, the biggest planet in the solar system, and it has the most mass. So this planet has more mass than every other planet in the solar system combined. Its great red spot alone, the giant storm that is currently on Jupiter, is about 3 Earths big. So when they said this is a massive storm, it is a huge storm. And Jupiter's full of small storms all over its surface. So it being a gas giant and being so large, it actually is one of the fastest spinning planets as well. And all of this speed throws around the gas inside its atmosphere and all over its surface to create these huge storm clouds. You can actually see some in the detail of this image here. About here, we can see this darker band across Jupiter. So you can actually tell approximately the height of each band on Jupiter's surface. So if it is a darker color, it's going to be lower in Jupiter's atmosphere, and if it's a brighter color, it's going to be higher. Jupiter, as Mr. Dorman said, is mostly hydrogen with some other elements like helium, ammonia, methane, and even some water too. All of these hit each other in these massive storms and creating chemical reactions that give Jupiter the beautiful color it has now. And so these bands are also rotating at different angles, I suppose. Because of something called the Coriolis effect, Jupiter's spin pushes these to rotate sort of almost against each other. So each band is going in the opposite direction than the one before it. So you have these clashing storms constantly that just feeds into the chaos of this planet, which actually helps keep the Great Red Spot going. On one side, it's got this wind pushing towards it, and on the other, it has the opposite, so it keeps it spinning. And the winds on Jupiter can get up to about 400 miles an hour. This was measured by the spacecraft that we sent to Jupiter, and at the end of its journey, we actually decided to crash it into Jupiter to try and get a little bit more data than we could in order to honor this probe's death. And so it is absolutely amazing how much of this planet is so fast, so chaotic, and beautiful at the same time. Like they said, as you go outside tonight, you can actually look up and see Jupiter and Saturn in the night sky. The brighter of the two will be Jupiter, and then just above it and to the left will be Saturn. These will stick around for quite a bit longer, so if you miss it today, don't worry about it. You'll be able to see it again. And yeah, so without further ado, I'll pass you guys over to check out Saturn.
Maybe I'll show us again where we're going in the sky for this and then bring you up. Okay. Hey, thank you so much, Austin. That was great. We are now again going to continue looking towards the south, and we're going to move on to the next planet in our solar system. We're going to take a look at Saturn, also in the southern sky there. And so I'd like to introduce you guys to Olivia Tobin. She is a math and physics major here at the University of Iowa. Thank you, Olivia.
Okay, Hi guys, like Dr. Roberts said, I'm Olivia. I'm a math and physics student here. And we're gonna look at the next planet in order, as you learned from Cole, which is Saturn. So first we have to type in our coordinates, which, like Austin said, are kind of like latitude and longitude, but for the sky. Hopefully you guys are excited for this one, because I know in the poll a lot of you liked Saturn. And we should be able to see the rings. So you can see our telescope moving down here. It's getting a little darker there in Arizona. All right, so now we go over to our image. Wait for it to load. We're gonna look at it with a red filter. And since Saturn is really bright, we don't need to leave the camera open for very long because it can collect a good amount of light very fast. So we'll leave it at 0.1 seconds. Wait for it to load. All right, so this is Saturn. You mess with the exposure a little. Wait, a one? Okay. It's a little too bright, so we're gonna try less time. It's okay. Okay, here we go. Okay. All right, well, we might leave it at this. So here we're looking at Saturn, and right here you can see the rings. So some fun facts about Saturn. It actually takes light from Saturn about 83 minutes to reach the sun, and we're a little closer than the sun to Saturn, but the image we're looking at right now is actually Saturn over an hour ago, which is kind of weird and trippy to think about. And then once again, like Jupiter, although Saturn isn't as big as Jupiter, it's still huge compared to Earth. So if you put 9 Earths side by side, we would still not even be as wide as Saturn's rings. It takes Saturn about 29 Earth years to orbit the sun, but its day, so how long it takes it to rotate around its axis, is actually only about 11 hours. So it's rotating really fast around itself, but orbiting slower than Earth is. And since Saturn is so big, it, like Jupiter, collects a lot of moons. So it has at least 53 known moons, but there might be up to as many as 82. We're still finding new ones every day. So the part of Saturn that everyone cares a lot about are the rings, right? That's what makes it so exciting. And Saturn actually has 7 rings, which are, like Cole talked about, they're made up of chunks of ice and rock that Saturn's gravity has collected. And so we're lucky right now. Well, not too lucky. You can usually see Saturn's rings, but about every 29 and a half years, Earth and Saturn are at a perfect angle where we're just looking at the rings edge on. So it's kind of an optical illusion where we can't see the rings anymore, which is kind of crazy. And then my favorite fun fact about Saturn is that similar to Jupiter, we had a spacecraft called Cassini orbiting Saturn and learning more about it. And when it had done its time, we also crashed Cassini into Saturn and vaporized it in the atmosphere, which means that about 2 tons of Saturn's mass are accounted for by this spacecraft from Earth, which is kind of cool to think about. So that's Saturn. And next, we're going to look at Neptune. So, got to type in some new coordinates here. All right, so here you can see our telescope moving. It's got to move a bit longer for this one. So like Cole said, Neptune is the only planet that you can't see with your naked eye. And when we look at it, when you're observing images of the other planets, it's pretty easy to tell which ones they are. But with Neptune, it's so far away that it kind of just looks like all the other stars. So what we have to do is take a star chart of what that part of the sky would look like without Neptune, and then compare it to our new image with Neptune and try to figure out where it's different. So it's kind of like one of those little spot the difference things, but for astronomers. Okay. So since Neptune is farther away, we have to look at it for a little bit longer, leave the exposure open to collect more light. So we're going to do 3 seconds. And maybe we'll try looking at it in blue. Wait for it to load. All right. Oh, right. Okay. Oh, there it is. Okay. So this is Neptune, this little tiny speck right here. I'll try zooming in.
Sorry, I just let you.
Oh, no, you're fine. You can find it. Oh, there it is. Okay. So you can see why we might need a star chart to figure out that this is a planet and not just a star. Some fun facts about Neptune. It, like Saturn, also has rings, but they're very faint, so they're a lot harder to see. And so Neptune is actually about 3 billion miles away from the sun, which for a comparison, Earth is like 93 million miles away from the sun. Both are kind of unimaginable distances, but Neptune is 32 times farther away from the sun than the Earth. So that's why we can't see it with our naked eye. And Neptune is actually the windiest planet in the solar system. So where winds on Earth the top wind speed on Earth is like 250 miles per hour. And the wind on Neptune can get up to 1,200 miles per hour, which is actually faster than the speed of sound. So the wind on Neptune is breaking the speed of sound. That's how fast it's going. We had a derecho earlier this year, which felt like really crazy wind, but can't even imagine what it's like on Neptune. So, like Cole said, it takes Neptune a super long time to orbit the sun, about 164 Earth years. So actually, since we discovered Neptune through math, it has only made one full orbit since we found it, which is pretty crazy. And that was in 2011. And then Neptune has 14 moons, which are named after Greek sea gods and nymphs. And sometimes if you get lucky, you can see the biggest moon, which is Triton, but we cannot see it tonight, sadly. And then Neptune is also bigger than Earth, although not as much bigger as like Saturn or Jupiter would be. But if Earth was like the size of an apple, Neptune would be about the size of a basketball. So still quite a big difference there. And then I know Neptune is technically the farthest planet from Earth, but sometimes because of Pluto's elliptical orbit, Pluto will be closer to us and the sun than Neptune, depending on its position. So yeah, this is Neptune, everybody. And next we will be talking about comets.
Thank you so much, Olivia. In just a second, I'm going to introduce you to Ashton Hooley, who will be showing us this comet. But very quickly, let's go back and review. So I need to clear our screen here. I think I messed you up. I'm sorry about that. It was totally me. Let me just clear this. Oh no. Hooray. Oh no. Oh, the wonders of Zoom. Okay, let's just refresh if we would. If we go out at night, right now perhaps, and you look towards the southern sky, you see Saturn and Jupiter. It's if you go towards the constellation Aquarius that you would find Neptune. But then, if we look in the direction of the constellation Ophiuchus, Ophiuchus in the southwest is where this comet we're going to see is located. So everything is in the southern sky pretty much that we're observing tonight. So with that, I want to introduce you guys to Ashton Hooley, who is also an undergrad here at the University of Iowa. He is a philosophy and a creative writing major, and he works for the physics and astronomy department, and we're so glad to have him here. Thank you, Ashton.
Hello, everyone. So let me get these coordinates really quickly off my phone. And I'm going to input them first and start getting the images ready, because these images are going to take longer than all of the rest to take. First one. Okay. And now we're gonna watch the telescope move to that location. It's going to be over here. So just like, well, not necessarily like Neptune, but this comet is actually quite dim. So in order to get the best photos, we're going to leave the exposure on for quite a while, which means the pictures are going to take about 4 minutes to take. And I think, so we're going to change the calibration here. We're going to change the exposure time to 120 seconds. As you can see, the telescope is now at the location, and we are just, well, let me change the filter really quickly. We're going to want the red filter here. The telescope's going to change the filters really quickly, and we're going to start. So, as Cole has said, this comet is from the Kuiper system, and the way we can easily tell that looking from Earth is because this comet has an orbit period of only 5.5 years. Now that is very short for a comet, and it's because it's so small, you can tell it doesn't come from the spherical asteroid belt, I guess. And when we get these photos, the only way you can tell a comet different from a star is from the haze around it. Now, as Cole said, the solar winds create a tail on the comet, and these tails consist of mostly ice and dust. Now, when we get these photos, we're going to be able to see this haze, and that's our only way to differentiate it from just the average star. So that's what we're mostly going to be looking for when we get these photos. This comet's closest approach to Earth was actually in 2006. So since then, it's come around 2 more times. Well, 3 more times if you include the one we are discussing right now. And unlike Jupiter, there's not a lot of facts about this particular comet, so I'm kind of running out here, if you couldn't tell. This comet in particular is called the Howell's Comet. It's not as known or significant as the Halley Comet or the Neowise Comet that actually just passed over the summer. It's actually still passing, but it's not as bright as the oh, hold on. The images are ready. Let me adjust the zoom here to see if we can see it around here. This, yeah. So we're gonna adjust this really quickly to see if we can find it. No. I am not seeing it. Okay. Oh, it went away. There it is. Yeah, because right now I'm not seeing it. So, okay.
Okay, well, it's a very dim object, and we can continue to, play with this some more, spend some more time on it, if you're able to stick around. But, what this really is just, an issue with the telescope. I'm so glad that Ashton got us started on this, and he did fantastic. Thank you. And so this is probably something on my end, that I did not think about. So if you can stick around, we will be here for a little bit longer trying to get Comet Howell. And, if you need to head out at the end of the hour, I just want to thank each and every one of you for being here. I want to thank all the undergrads who did such a fantastic job. And it's, so wonderful to have them here. Thank you to Cole for the talk and all the undergraduates who shared the astronomical images. And just again, thank you to every one of you who attended tonight. And we hope to see you at some of our later public observing nights. There'll be 3 more this semester, each with a mini talk and some observing. And sign up for it the same way that you signed up for this observation. Feel free to contact the Department of Physics and Astronomy if you're not sure where to find those links. We can get them to you. And again, we're gonna keep looking for Comet Howell. We saw it last night, and it looked great. And so I probably just set something up wrong here on the telescope, but we're hoping we'll get it. And if you can't stick around, that's totally fine. And we're so glad to have you here. Have a wonderful night, everyone.
Or the 9 o'clock coordinates? Because I put in
Yeah.
the 8:55 original.
Maybe so. One thing that's particularly puzzling to me is usually this is toggleable, and I'm just really not able to get stars to pop out in the way that I'm used to. And so I really do almost feel as though it's maybe like a settings issue or something.
Yeah, maybe.
Just like see if we see stars sort of thing. I mean, obviously we see stars, but see stars in the way that I'm used to being able to change the content. Yeah, it looked great.
Yeah.
It must just be something in the settings or something. Yeah. I'll have to get your coordinates again. I just wanted to go off field for a second. I just went to a star. Oh, because it got saturated. There was so much light that it like bled out into Okay, could you give me the coordinates again?
Yeah.
I feel better about how the image is appearing now.
Okay, 17 hours, 21 minutes, 41.8 seconds. Oh wait, no, 42.6 seconds.
Okay. Perfect.
-26 degrees, 55 minutes,
Awesome.
47 seconds.
Perfect. Thank you. Oh no, we lost it.
Oh my gosh, did the horizon? Oh,
It did, it did. Oh man, that's too bad.
yeah.
Okay, thank you everyone who patiently waited. Very unfortunately, this target is quite low and it has set so far that our telescope is no longer able to point to it. So I apologize. We won't be able to see this comet tonight, but what we'll possibly try to do is if you're able to attend our next public observing night, we can maybe start the night off with the comet if you're able to come that evening. But I really appreciate you guys hanging on and trying to see it. What I will do right now is I can show you an image that we took of the comet last night. It's not quite as good, but hopefully it might still be interesting to see. So if you give me just a second, I'll pull that up. Okay, so last night Ashton Hooley took this picture of the comet Howell, and so this is what this comet looks like right now. He imaged it just last night. and we just had some difficulty with our camera settings this evening. But this is the comet. And as Ashton was talking about, you can see that it's sort of fuzzy. It's got this gas and dust blowing off of it. Unlike the other stars, right, that we see in this image, we can see the fuzzy nebulous appearance of the comet. So we used this exact same telescope last night, exact same camera, took this picture. So this is what we would have seen if our camera was cooperating this evening. But that does finally conclude our program. Thank you so much to everyone who attended. I'm very grateful to the undergraduates and very grateful to you all for being here. Have a wonderful night and a wonderful weekend.